All right, so sorry about the lack of video. My name is Sriram Shankaranarayanan. I am a professor in the computer science department, and it's my pleasure to introduce Professor Majid Zamani. Majid has been with CU Boulder as an assistant professor since 2018. So previously, he was a assistant professor at TU Munich, and before that, he did a his postdoctoral work at TU Delft in the Netherlands, and before that, his PhD from UCLA. Majid's work is on synthesis and verification of autonomous systems. He comes from a background that combines ideas from control theory and formal methods in computer science. Majid's work has been recognized in many ways. One notable award that he has won is the ERC Starting Grant, which is the European version of the US Career Award. Except that it's about 3 times the money and 3 times as competitive from what I'm told. So I will let Majid tell us more about the work he's been doing here at CU Boulder. So take it over, Majid.
Thank you, Shriram, for the introduction. It's my great pleasure to be here today and presenting about the research we have been doing in the last few years regarding analysis and design of autonomous systems. And good afternoon and good, I guess, midnight to some of those who are attending from Europe. So I hope the talk will be exciting for all of you. So what is the title of the talk? Is about breaking the curse of dimensionality in designing autonomous systems. So first, let me introduce what do I mean by autonomous systems. I mean, autonomous systems are the one that I'm dealing with are those which are a combine of tight interaction of physical and computational components. So of course, self-driving cars are an example of autonomous systems, but here in this talk, I mean in a very general perspective of autonomous systems, and they are becoming more and more ubiquitous, which we know why, because we have seen a lot of advances in both computation, memory, and communication capabilities. Example of those systems include self-driving car, transportation network, smart grid, and robotic manufacturing. So, but on the other hand, so these systems are becoming more and more. But the problem we are facing is they are also becoming very complex. And the complexity is due to the reason that, so we see more and more computation and communication components are interacting with the physical components. And this tight interaction actually will cause complexity in designing and analyzing these type of systems. So the reason is because computational components usually have discrete nature, and then physical components, for example, controlling velocity, acceleration, temperature, density, so on and so forth, they have physical evolution. So, and these two different, let's say, components are interacting with each other in a very tight way, and that's make it very difficult to rigorously analyze these types of systems. And they are becoming more and more autonomous. They are taking decisions on their own without human involvement. And that's actually the goal of making them more complex, because we want them to make their own decisions and hopefully in a correct way. And that's going to be the focus of the talk today. But there is a but here. And the reason is because mostly these systems, because they are very complex, they're still being designed in an ad hoc and heuristic way. And that's not good, because this can cause catastrophic events. In particular, if we are dealing with safety critical applications. So I'm sure most of you are aware of the Uber fatal autonomous car crash, which happened in 2018. And unfortunately, a pedestrian got killed in this crash. And the driver, actually, she was convicted by negligent homicide. And she was actually watching a TV show on her cell phone while she was behind the wheel. So the interesting part about this example is this is not a corner case or rare case in self-driving car. And in fact, the collision avoidance design in Volvo XC90 would have prevented this crash. And Uber, while they were actually designing their self-driving mechanism, they actually disabled the collision avoidance, which was coming by default in those SUV cars, which would have prevented this crash. And this was, and there was no, like the radar detected the pedestrian perfectly, but the car decided to brake only 1 second before the impact, and that was already too late. So my research is, I'm trying to, hopefully the main goal of my research is actually preventing these type of accidents and crashes and a failure in safety critical applications. So let's see what's going on now and what is the practice today for designing autonomous systems. So almost most of the self-driving car companies and even the other companies working on different aspects of autonomous system, they are actually relying on testing. So they say, okay, let's test our autonomous systems and using testing, try to convince customers that we have a very reliable systems. The problem with the testing is, based on a study done by Kalra and Paddock in 2016, so if we want to have this with confidence of 95%, if we would like to design an autonomous self-driving car with the same performance as human driver in the state of Colorado. And the reason I provide the state of Colorado, because different states, they have different statistics. In a state of Colorado, the fatality in car crash is 1.09 in every 100 millions of miles. So in order to reach to the same performance with the confidence of 95%, we need to have 275 million failure-free miles to demonstrate the same performance. So let's see, what does it mean? So that means 12.5 years with 100 test vehicles driving 24 hours a day. And here I assume that the cars are being driven on average 25 miles per hour. So as you can see, this is costly, time consuming, and still they are not safe. So, and also keep in mind that, so you do all this, let's say it's doable. Let's say we can do this test and we can reach to that confidence of 95%. The problem is the moment you start updating your software, the moment you start updating the hardware being used inside your autonomous systems, the guarantee that you were able to provide using the test does not carry over. So that means you need to start doing testing again from scratch. So, that's not doable, right? So, okay, let's see what we are proposing to do for designing autonomous systems. So now I'm becoming more and more specific. So what do I mean, and what are the goal of the research we are doing? So let's look at the core of many of these autonomous systems application. So what do we see? We see a physical system, which usually described by some sort of differential inclusion or difference inclusions. So how do we come up with those models? We just write Newton's law, and then we are able to come up with this mathematical model. And then we have some sensors that measures the state variables of the system. For example, in the case of self-driving car, the velocity, acceleration, and other variables in the system. And they feed those measurements to the computer of the, for example, in the case of self-driving car, let's say the autopilot. We call it embedded controller. And then the embedded controller, given the property of interest, tries to control the actuators of the physical system. So the main goal of my research is designing this embedded controller for the physical system in a formal and rigorous way, and at the same time systematic. We don't want to resort to manual design and writing equations on a paper and try to prove manually. So that's also not doable given the complexity of the autonomous systems we are facing. So what are the main objectives that the embedded controller has to enforce over this closed loop? So, for example, what we are dealing is complex temporologic properties, and these are actually very rich types of specifications, and many of the property of interest for autonomous systems can be represented with these logics. And for example, in the case of self-driving car, you say, design a controller that enforce the car to respect traffic signals or respect the speed limits. So these types of properties, which are very close to human language, they can actually be written in a formal and unambiguous way using temporologic properties. And the design goal is we would like to synthesize, hopefully algorithmically, the embedded controller, which is going to be a code implemented on this digital platform, such that the closed loop satisfy these high-level control objectives. So, and this is very challenging. And the reason is because we are dealing with a heterogeneous closed loop. I have physical quantity, I have digital components in this closed loop, and the property of interest are also heterogeneous themselves. So in the remaining of the talk, I will actually try to provide some methodology on how we can actually design these embedded controllers for possibly larger scale autonomous systems. So in order to convince you that this temporal logic which I introduced here is good enough for deploying autonomous systems, here I provide a very simple example of autonomy in transportation. So let's say you may say the autopilot that I designed should enforce safety rules. And what are those? No collision or obeying a speed limit. So you see, these are the corresponding linear temporal logic properties for these safety rules, which can be written very easily using these types of logics. And the autonomous car should also satisfy some goals or liveness properties. For example, the car should eventually, because the safety rules are satisfied if you put your car in the garage and don't drive it, right? But then there are some liveness aspect in the property as well. The car should reach at some point to some target point, maybe dropping point for dropping the passenger. And after dropping, the car should go back to maybe a starting point. And we can also model the assumptions over environment. For example, each intersection hopefully is clear infinitely often. So this can also be represented using temporal logic. And the goal in this particular example is we would like to design the autopilot that enforce these high-level temporal logic property, which says, assuming that considering the environment assumption, the autopilot or the controller should enforce safety and goal objectives. Okay, so here in this talk, I actually will propose two methodologies. One is abstraction-based, the other one is abstraction-free. So let's first look into abstraction-based. So in the abstraction-based method, which called symbolic methods, so what do? Is we said, okay, we have a continuous dynamics representing the physical variables in the autonomous systems. And these are evolving in a continuous domain. And at the same time, I have also some discrete variables which are modeling the computation and the software components in the autonomous systems. So in order to be able to analyze them at the same time, so what we do is we say, okay, let's actually lift the continuous dynamics and build a discrete representation of that. We call it discrete abstraction. And I mean, the main question is, of course, how do you go from continuous dynamic to discrete? I will briefly explain that in the next slide. But let's say I'm able to rigorously build a discrete abstraction representing my original continuous dynamics. So now, since I have a discrete system, so what I can do is I can just compose the discrete abstraction representing the physical part with a discrete abstraction representing the computation part, and everything is now discrete. And now the good news is I can actually use reactive synthesis, which has been developed in the CS community, in the formal methods community, and design a discrete controller to enforce some high-level property here in this discrete domain. And at the very end, I just refined the discrete controller to something which is applicable to the original autonomous systems. And this controller by nature is going to be hybrid. Why? It has some discrete variable in it, as well as it also gets the measurements from the autonomous systems, which are continuous variables. So by nature, this controller is going to be hybrid. But the good news is, by following this diagram, I have formal guarantee that this hybrid controller, when it's applied to the original continuous dynamics, will actually enforce the same property which I was able to prove in the pure discrete domain. So that's the beauty of this method. Every step comes with formal guarantee. So at the end, the final product, I have a mathematical guarantee that it works if it's being applied on the original continuous dynamics. Very nice, everything comes. And the other thing is the design of the controller becomes systematic. You ask the computer to formally design the controller or design the autopilot for the self-driving car without the involvement of the human designer. So the computer will take care of designing systematically the autopilot code for the self-driving car. So that's the beauty of this approach. So now, very briefly, you may say, how do you go from something which is continuous, evolve in an infinite set, to something which evolves in a finite set? So the idea is actually very simple. So if you have let's say my physical variables evolves in two-dimensional space, so what I will do is I just put a grid on the state set, and I put a grid on the action set. And then for every cells of the grid, and for any given control action, which is also finite, I compute the over approximation of the reachable set along the flow of the physical system. Remember, it was modeled using some sort of differential or difference inclusion. I just compute the over approximation of the reachable set. So this set is modeling all possible states of the system that can be reached if the system starts from this square under a given control action after tau units of time. Tau is the sampling time for which the autopilot is operating. Yeah, the frequency that autopilot, let's say in the case of self-driving car, is operating. So now what I will do is non-deterministically, I put discrete transitions from this discrete state to these 6 discrete states. And I continue this, and I have a finite automata representing my continuous systems. And I can guarantee that these 2 systems, one is finite, the other one is infinite, they're actually formally related to each other. And I can even guarantee that if I design a controller on that discrete object, and I refine the controller over the original continuous space model, the property are preserved. So that's the whole point of this going from continuous to discrete. We need to be careful that if you do any sort of analysis over the discrete domain, we need to ensure that analysis and that proof carry over to the continuous domain. That's the tricky part here. Because if we lose the proof in any of these going up to the discrete and coming back to the continuous, so then we lose formal guarantee. But we are able to ensure that in all these steps, the proof carry over from continuous to discrete and discrete to continuous. And this method of building the abstraction is independent of the way I computed the over approximation of the reachable set. If the reachable set, Shriram has done a lot of work on reachable set calculation. They have a tool called FlowStar. So you can use any off-the-shelf reachable set computation to come up with the tightest possible reachable set for your physical system. Then you get a less conservative discrete abstraction. And hopefully you can find a controller when you start searching in the discrete domain. for a controller given the specifications of interest. So yeah, that's how we build the discrete abstraction for physical systems. Good news, we actually developed a tool called SCOTS. So what are the input to the tool? You give a mathematical description of your physical system, differential inclusion, difference inclusion. You give the property of interest. So SCOTS natively support safety, reachability, reach and stay while avoid. And in fact, SCOTS has implemented minimum and maximal fixed point. So you can actually use combination of these two fixed point algorithms to actually synthesize controller for even more complex properties. So, and then you provide those quantization parameters for the state and input set, and then you just push a button. SCOTS will design, will build, will construct a discrete abstraction, and will design a controller in the form of a binary decision diagram or sparse matrices. There are different data structure being supported by SCOTS. So SCOTS actually has been one of the main tools in the hybrid systems community. Researchers are actually benchmarking their methods using the SCOTS, and they are actually comparing their method with our tool SCOTS. So after SCOTS, then me and my PhD student Mahmoud, we said, okay, let's actually apply distributed data structure and parallelization. What if I would like to use GPU? What if I want to do the calculation over FPGA? And that's actually what Google is doing for their search engines. Some part of the search engine of Google is actually happening over FPGA. Or I would like to use cloud computing for do all these intensive computation. So we designed a tool called P-Faces, which actually support all these different sort of computing platforms. And the good thing about P-Faces is being developed in a generic way that you can actually use this orange part for any other purposes that you want to, for example, parallelize your own, let's say, algorithm. The purple part is the kernel that you need to feed inside P-Face. For example, in the case of symbolic control, we developed the symbolic control kernel. And then colleagues in Berkeley, they say, oh, we would like to use this for reachability. So great. So just provide a kernel for reachable set computation, which the tool is called PERC. And using PERC, for example, we are able to compute reachable set for differential equation up to 1 billion dimensions. So, okay, let's see how can we use symbolic control in action. So with the help of Autonomous Systems IRT, we got a funding to establish a lab. And then we had a Maddie, which is she's an undergraduate in our department. With the help of Mahmoud, they start establishing this platform in our lab at CU Boulder to actually deploy Amazon Deep Racer car using symbolic control technique. So first, we modeled the AWS Deep Racer mathematically. And this is the model of the robot. It's a 4-dimensional differential equations. We did a bunch of identification to identify these parameters A and B, and we came up with a very nice and good model for these robots. And you see, we can actually project the arena using 4 projectors, which is being mounted on top of the platform. We can actually dynamically change the environment. So that's a good thing about this platform. And then we said, okay, let's use P-Face, design controllers for Deep Racer and deploy it autonomously. Before I show you some video, let me give you some numbers so to get an idea of what's happening. So for this example, for this Deep Racer in this arena, so the size of the abstraction, discrete abstraction has over 6 million discrete states. And it has around 800 million transitions. The number is big, but look how long does it take to compute the abstraction? 40 milliseconds to build this abstraction, which has around 800 million transitions. And how long does it take to build the controller? Around 200 milliseconds. And this is all happening systematically, right? We just push a button, we have a controller. So, and then we said, okay, let's actually, given that things are happening fast, let's deploy the robot, and Maddie will come and just put some obstacle that robot didn't know in advance they're going to be obstacle on the field. But what we do is we just resynthesize controllers on the fly. From scratch, we design the controller on the fly because it doesn't take that much time. We are able to do that in every cycle of the control action. We are able actually to resynthesize the controller from scratch, given the new arena. If there is an obstacle. So let me show the video. So the robot is supposed to reach green region. So now Maddie comes and all of a sudden introduce an obstacle, which robot didn't know there's going to be an obstacle. But on the fly, robot realize that there is an obstacle, the controller get resynthesized, and with the new controller, the robot is able actually avoid obstacle and reach the green region. So now here, Maddie is trying to make it more complex. She's moving the obstacle and trying to confuse the robot and see if the robot is able to actually reach the green region. And you see, because the robot is actually resynthesizing the controller on the fly, and it doesn't take that much time, so the robot is successful to reach the green region. So you may say, okay, things are beautiful, everything is systematic, you just push a button, you have a controller code. In fact, we have a code which being generated even with guarantee. So we generate the code, you can actually put the code, it's a C code. You can actually write, either you put it in the computer you have, or we also generate the Verilog code in case you want to implement it on FPGA. But then there is a subtlety here. Things are not that beautiful. And the reason is, as you can imagine, the size of discrete abstractions grows exponentially in the number of state variables. And that is called curse of dimensionality. And that is preventing us from applying symbolic control to real life applications, which has physical dynamics, which are large scale. So now, rest of my talk is about how can we break this curse? How can we make symbolic control applicable to large scale systems? So I use two ideas to break the curse: aggregation and compositionality. So in the aggregation, so what do? We said, okay, so you have a physical system. See if you can aggregate some of the state variables. I'm talking about continuous state variables, and represent them by one state variable. So this is also called model order reduction. In the continuous domain, we try to see if we can reduce the dimension of the physical system. So the way we do it is, I assume my autonomous system is given as interconnection of bunch of components, which these components are also physical components, and M represent the topological, the topology of the interconnection. So now we are able to actually provide an aggregation or a reduced order model of each of those components and a new topology for which we know the output in the aggregate domain or the reduced ordered version mimic the output of the original continuous dynamics. This is called infinite abstraction. And the reason we call it infinite abstraction because the abstraction happens in the infinite domain. The abstractions are a still differential equation. So now we go one step more. Said, okay, now let's build finite abstraction of components and the topology such that when you compose those finite abstraction, this whole thing is a finite abstraction of the original interconnected system. So we provide guarantee, we provide some conditions under which this is happening. So you see, I break down the problem, I provide a divide and conquer strategy for which I bring the complexity of the whole interconnected system to the level of complexity of subsystems. So now I have a discrete abstraction for a larger scale system. I can do what I did before. I can actually design discrete controllers for the finite abstraction and then refine it back all the way to the original system. And again, I emphasize here, I stress that all these steps from here to here, 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 here happens with mathematical guarantee. So we do not lose any formal guarantee going up and coming back down. We are able to actually track all the errors we are suffering and provide quantitatively that so you see, I designed a discrete controller here which guarantee that this closed loop at the very top layer, which is all discrete, satisfies some specification of interest. So with following this methodology, I can guarantee if you apply this controller, this object here, to this original larger scale interconnected autonomous systems, this closed loop will also satisfy the same specification which was satisfied at the very top layer in the discrete domain. So in order to provide infinite abstraction, the way it works is we look at the original interconnected system, and then we go and look at the subsystem level. So we are able to provide an aggregate subsystem or a reduced order version of sigma I. If it's linear, we provide geometric condition. And for some classes of nonlinear system, we are able to actually construct the reduced order model such that there is some property between these two. And then we are able to provide some compositionality condition under which you just need to connect those reduced order model with a new topology called M hat, and we know how to build M hat using M, for which this interconnection is somehow mimics the behavior of this interconnection. So now, rather than working with the concrete interconnection, you work with the virtual interconnection, and you try to build the abstraction for this virtual interconnected system. And in the next phase, what we do is we said, okay, but infinite abstractions may not be useful on their own because I would like to provide systematic approach designing controller. So I need finite abstraction, something which is discrete. Okay, so what we do is we use those infinite abstraction, and now we do the same thing. We build finite abstraction of the component. We provide conditions under which composition of finite abstraction is a finite abstraction for the interconnected, original interconnected systems. So let me apply this idea of parallelization using p-phase and also some sort of sparsity in the dynamic, which I present in the form of interconnection of component, on a rigorous example. We applied the method on a 7-dimensional BMW 320i model. This is the mathematical model of the BMW. And you see, we are actually considering yaw angle, slip angle. So this is a good model if one is interested in crazy maneuver of the car. And the specification is the car is driving on the lane, and then there is a crash, all of a sudden happens in front of the car. The car should autonomously avoid colliding with this collision, and then come back to its travel lane after avoiding colliding with these cars. So here we tested our experiments on 3 different hardwares. One was our local machine, and then 2 of them on AWS server. And these are the numbers you see. So, and by the way, you see the size of the abstraction is in the order of 23 billion transitions. So, and these are the, how long does it take to build the abstractions together with the controller for these types of specification over these model of BMW 220i. So if you're interested in the details of so the parameters are coming for this particular car. So you can actually look at the parameters in this paper. So far, I talked about one approach which requires discretizing the state set. So there has been different techniques in the past decade which actually advocate different methodology, which doesn't require discretizing the state set. And they call it barrier certificate. So let's see how does it work. So let's say I have a system sigma described by this recursive equation, nonlinear, and I'm given 2 sets. X0 is the set of initial point, X1 is the unsafe set. So if I'm able to find a function B for which in the green region, B has to be less than or equal to 0, in the red region, B has to be positive, and along the dynamic, B is non-increasing, then we have a guarantee that my physical system is starting anywhere inside the green region. As time elapses, the physical trajectory of the system never reached the red region. See, without discretizing the state, by just finding this function, we are able to provide this mathematical guarantee that the system will not enter the bad region. And for the record, this paper, which introduced this idea for the first time in 2004, this year got the Test of Time Award during CPS week. So the previous slide was talking about verification. If we find the function B, we can verify the system never entered the bad region. We can also extend it for the case of designing the system for which will not enter the bad region. So for that, I added this extra variable upsilon, which plays the role of input to the system, for which I can influence the system. So now the first 2 conditions are the same as before. The only difference is in the last condition. You see, for any state X, there exists U. This existential quantifier is actually incorporating the role of designing the controller, for which barrier is non-increasing. So in this case, there is a controller K, which enforces the system, if it starts from green region, enforces the system not to enter the bad red region. So, okay, you may say barrier looks great. You just search for a function. How bad can it be? Actually, searching for that function is also a hard problem, yeah? There is no free lunch. So under some assumptions, if your dynamic is in the form of polynomial, people actually provide techniques on searching for those functions. For example, by resorting to sum of a square optimization. And there are some tools that you can actually search for sum of a square type barrier functions. And the complexity, if the degree of the polynomial is given, and if you assume the barrier is in the form of polynomial, it's polynomial time. In fact, Shriram has done a lot of work on searching for barrier functions using called counterexample guided inductive synthesis. So with his previous PhD student Hadi, they use SMT solvers to search for barrier functions. And they don't need any assumptions on the dynamic, which has to be polynomial. But the problem is, in the worst case, complexity is exponential time. So now you can imagine, if I have a large scale system, again, even in this case, which I am not doing any discretization, I am still suffering from computational complexity. So now the question is, how can we tackle this complexity in the case we are searching for a function? Again, we can do compositionality here. We can do divide and conquer strategy also in this case. So how does it work? Let me give you an example of a system composed of two subsystems to see how does it work. Look, I have a system sigma composed of components sigma 1 and sigma 2, which are connected to each other in a circular way. The output of system 1 comes as an input to system 2, and the output of system 2 goes as an input to system 1. And look at the dynamic of each subsystem. You see, W1 and W2 plays the role of exogenous input, environmental uncertainty. The input provided by the environment plays the role of uncertainty. But on top of that, I have also, you see, a state variable of other subsystems affects your dynamic. Do you see here? So now what I will do is I will not search finding barrier for sigma. What I will do is I try to find some sort of function. I don't call it barrier because they are not really barrier. They cannot ensure anything, but they have some nice property. I search for functions B1 and B2. Look, the first two conditions exactly the same as before when I introduced barrier certificate. But look at the last condition. It says barrier for subsystem I along the dynamic of subsystem I, which has the effect of the state of the neighboring subsystem, is bounded by these two terms. The first term is the barrier at X. X is the state of my own subsystem. And then again, rho I times norm of the state of my neighboring subsystems. Now look at this beautiful compositionality condition. It says if rho 1 times rho 2 is less than 1. It doesn't say that what is the amplitude of the state of the neighboring agent. It doesn't care. It only cares about the gain. If the multiplication of two gains is less than 1, then the monolithic system is safe in the sense that if it starts in this Cartesian product of the initial set, it never reached the Cartesian product of the unsafe set. And look at here, those gains, one of them can be very large. I'm not assuming that the gain for which the systems interacting with each other, all of them has to be small. If one of them is very big, the other one has to be small. That's what this compositionality condition is telling us. So what we did, we said, okay, let's apply this to the general interconnected system with a general interconnection topology M. So what we do is we build, we call it sub-barrier function for the components, for the subsystem in this large scale autonomous system. And then we provide compositionality condition. In CS community, they call it circularity condition, for which you can actually combine those sub-barrier functions of subsystems, and then you can build a gigantic barrier functions with the guarantee that it's a barrier functions for the interconnected system. How do we compose them? There are two approaches. One of them says just take linear combination of those barrier function, and under some compositionality condition, it's going to be barrier for the interconnected system. The other approach is says takes the maximum of those functions, and under compositionality condition, that is going to be a barrier function for the monolithic interconnected system. Let me apply this on a very simple example. I have a room temperature control problem. I have a gigantic building consisting of 10,000 rooms. And these rooms are connected to each other in a circular fashion. And this is the dynamic of how the temperature in each room is evolving. So, and this is the specification of interest. It's given in the form of a deterministic Kobuki automata, which says if the temperature starts in P0, it should not go inside P1 or P2. So we are interested to finding polynomial type sub-barrier functions for each room. We use SOS tool and we are able to build, you see this BI of X, this is a sub-barrier function for one room. And we assume all the rooms are homogeneous in terms of dynamics. So the same function works for all of them. And we showed that the compositionality condition hold. So now if I take maximum of this BI, that for sure is a barrier function for this, the whole building consisting of 10,000 rooms. And this is the simulation. We show the maximum of the temperature and the minimum of the temperature, and the temperature of all the rooms evolve between these two max and mean, which shows that the specification is satisfied. So you see, I paid the complexity only for a scalar system because each room is a scalar. And then I was able to provide a barrier for the whole interconnected system, which has 10,000 dimensions. So what are the future work we are looking at? And in fact, we have already some preliminary results. So far, everything I explained up to now assumes we have mathematical model of the physics. Keep in mind, I can allow for uncertainty. You see, these are inclusion. But the uncertainty is also structured, and I know the set of uncertainty. But what if the model is black box? What if somebody gives me a Simulink model and I cannot see inside that box? The only thing I can do is I can only collect input-output data from the system without knowing what is the mathematical model. Can I look at the sample data? And given a logic specification, can I design the embedded controller? That's what we are now trying to answer without knowing the mathematical model by just collecting data. We were able to answer the verification question, not designing the system, but verifying whether a black box system satisfies some logic properties. We are able to provide some partial answer to that, and we are actually looking now into the synthesis as well. The next direction we are looking is, so far I talked about mission objective, safety requirements, and I didn't say anything about the security and privacy of the closed loop systems, which are increasingly becoming very important given all these cyber attacks which is happening in the past few months and all these ransom. And so the question is, can we design the controller which not only ensures the safety of the system, like no collision, it also makes the system opaque against malicious observer and intruder? So can we combine them and design a controller in one shot? So for the verification, again, we are able to provide some answer. Can we verify if the cyber physical system is opaque with respect to malicious observer? And now we are actually looking into, Shadi, my student at Boulder, she's actually looking into designing controllers using idea from control barrier functions to actually ensure opacity over closed loop dynamic. And that brings me to the end of the talk. So yeah, I would like to thank all my current PhD and postdocs, which I had the privilege to work with them. They're all brilliant researchers, and also the past PhD and postdocs in my group, and also many colleagues and bachelor and master students, which I had the opportunity to work with them. Unfortunately, the list is long and I couldn't put the name of those bachelor and master students. And Last but not least, I would also like to thank the funding agency, both in Europe and in the US, for providing funding to do all these cool researches about autonomous systems. And thank you for your attention.
Well, let's thank the speaker virtually. We have about 10 minutes left for questions. So, just unmute and ask the question. If there is the contention, I will try and resolve it. So maybe let me start. If there are no immediate questions, let me start the ball rolling, Majid. Thanks for the great talk. I mean, I see where you're going with this, but one thing that I wanted to ask you about was, you assume that there is sensing that's taking place and you're able to construct the state of the system. From everything I saw, you're using full state feedback. So how do you talk about, using like camera and LiDAR inputs to somehow, reliably get to the state of the system, which is often a big problem that breaks a lot of these guarantees. So can you talk about that?
Yes, thank you. That's a very interesting question. Yes, most of the talk was about assuming that full state information is available. But as you mentioned, in reality, we don't have access to the full state information. And sometimes we have partial information, right? So actually with one of my students, Nilufar, you see in this reference, I don't know if you can see the cursor, right? So what we do is we said, okay, let's assume I have partial information. But we assume that we are given an observer or estimator which is able to estimate the state of the system. However, we don't need to assume anything about the estimation accuracy for now. So what we do is we actually combine the dynamic of the estimator with the dynamic of the original system. We lift the system we make it twice as big, right? Because we combine both models. And then we search for control barrier functions over this product space to feed controllers by assuming that controller is only a function of estimated state, not the actual state. So that's the work which appeared in last year in IEEE control systems letter. But as I said, we assume the observer is given to us, and we haven't done rigorous investigation ourselves on how to design the observer. If you give me the observer, I can actually search for a controller using control barrier certificate based on the state of the observer, not the actual state of the system.
John has a question on chat. Would you like to tackle that?
Yes. So John is asking, in the control of the BMW, how much smaller and quicker did the reduced order model produce? How much did the performance of the closed system change? Very good question. In the case of BMW, we did not do any model order reduction. We dealt with the 7-dimensional difference equation directly. And as you can see, the computation time were not that much impressive. Like the best case, it was like half an hour for designing the controller. I mean, building the abstraction and designing the controller. We didn't do any model order reduction. We used the parallelization and compositionality only for the discrete abstractions.
Okay, so John has a follow-up, which we'll take. It's about losing the slip dynamics for the BMW. And then Ryan has a question on chat as well.
We do not lose the slip dynamic. This is the dynamic we deal with, John. We consider this dynamic completely. We do not ignore any of these states. We consider all of them, right? So, and then Ryan is asking, with regards to the subcomposition of the rooms in terms of finding sub-barrier, is it more optimal to compute 10,000 sub-barrier with respect to one large barrier? Thanks. So look, I don't know if you have worked with any of these optimization techniques. You cannot search for a barrier for a system of dimension 10,000, or at least it's not easy. So what we do is we said, okay, I know that this 10,000 dimensional system can be break into composition of 10,000 scalar subsystem. If the subsystem is a scalar, so now I can deal with the scalar subsystem much easier using sum of a square optimization. And I can search for a subbarrier functions for a scalar, and I can find it much easier than searching for a barrier for 10,000. So there is a complexity with the dimension. So we are not able to search for a barrier for a 10,000 dimensional system. So that's the reason we need to break it down to the level of subsystem, search sub-barrier, and then compose the barrier. And then we can ensure that their composition is a barrier for the interconnected system. Does it make sense, Ryan?
Yeah, thanks a lot. That makes a lot of sense. So if I understand it well, there was a theoretical like formulation that when you find the maximum of those 10,000 sub-barriers, that implies that you have found the barrier for the whole system. Did I understand that correctly?
Yes. So, but look, there is a condition. I didn't go into the math. If you're interested, we can talk offline. But there is a condition. Look at the case of interconnection of two subsystems. Look at the condition. Look, by the way, this is very similar to what is called a small gain condition introduced by James to investigate a stability of interconnection of two linear systems in 1950. So you see, it's very close to what people have done in classical control to ensure a stability of interconnection of linear system. So you see, our condition is very similar. So in the case of two subsystems, this is the condition. If you have more than two, so how does it work is you need to go look at the topology of the interconnection. Everywhere you have a cycle, you walk over the cycle, you compose the gain of the corresponding subsystems as you walk in the cycle, compose the gain, and the composition of the gain in that cycle has to be less than 1. That's the condition, which I didn't elaborate here. If that condition now holds, you take the max, that's the barrier. We have a guarantee.
Maddy asked a question. Let's try and address this question. It's on chat.
So yeah, do you redesign controller dynamically in each loop or update it with some learning method? No learning. With all respect of colleagues doing learning, we would like to stick with mathematical guarantee. So what we do is we redesign the controller using reactive synthesis. So look, you have an abstraction. Abstraction, you don't need to recompute, correct? The abstraction remains fixed. You compute it offline one time. The controller is search over a graph of the abstraction. And that also takes around 100 milliseconds. So we are able to do that. So we just resynthesize the controller. It's game over graph, right? And then we compute the new controllers given the new environment. There is obstacle. We just redesign a controller algorithmically. No learning involved.
So let me ask a slightly higher level question, Majid. I mean, one of the problems with embedded systems is code bloat, right? So if you're going to design a controller where you have millions of states and millions of transitions, your controller is going to look like a mess, right? With millions of if then else conditions saying if this then this, right? How do you manage, so in a software engineering flow, people don't like to look at that kind of code. How do you then work with get people to work with that code, right? Have you looked at those kinds of issues like power, code bloat, all those issues that people in embedded systems worry about?
Yes. So very interesting question. In fact, I had a discussion today with one of my PhD about that in Germany. So he said, look, there are SD card which already of terabyte capacity. Why should we worry about the memory consumption? But then I said, but accessing that memory can be an issue, right? Mm-hmm. So we actually have done a work which appeared 2 years ago in HSCC with colleagues at TU Munich, Jan Kretinsky, you may know him. So we used classifier techniques from machine learning community to actually represent the controller as a decision tree. We try to cluster those states because the controller at the end of the day is a lookup table, correct? So we are trying now to provide, I mean, if you look, it's like we are providing a coding fashion. We are trying to reduce the size of the controller using classifier techniques. But there is a trick here. The fitting should be exact because we don't want to lose formal guarantee of the controller when you apply the classifier, right? Because when you classify and you come up with a small decision tree, I mean, we have very interesting example of a gigantic lookup table, and then it boils down to a decision tree of like 5 or 6 states for an inverted pendulum example. What we care is we need to ensure that the formal guarantee of the controller is preserved when we do this classification in order to reduce the size of the controller. So we actually have a toolbox called DT control that does that. And in different contexts, my postdoc Mahendra is actually using that to design coder and decoder for in the different contexts, like in the context of information-based control to compute entropy of the dynamical system. So these are all very related. And in fact, Jan extended those work in the case of even Markov decision process as well.
Very cool. So we should, thank the speaker once again and, end this formal talk, but people who have more questions for Majid are welcome to stay back and talk with him if Majid can stay back as well. Thank you, Majid. Thanks, everyone.
Thank you.